Hello friends, welcome to Science Team. We have seen that in relativity, the Galilean relativity says that laws of mechanics are same in all inertial frames, but in special relativity we find that laws of physics are the same in all inertial systems. So it tells only about laws of mechanics and it tells about whole of physics. So you know that when we differentiate the Galilean transformation equations, we get the Newtonian version of the equation, and that says that the forces acting in with respect to all inertial systems are same. But in special relativity, we will see that this is not the case. So there are basically two principles. The first is called the principle of relativity. This is the principle of relativity. We said about the laws of physics are not with respect to any frame, they are same for all inertial frames. The inertial frames are those frames which have a constant velocity. So, and the second is called the law of constancy of light. This is the law or the principle of constancy of light. This is the principle of constancy of light. It says that the speed of light is same for all observers. So I have already explained these things, but for those who are seeing this for the first time, now you have a cart which is moving with some velocity, and you just you throw a ball. Okay, you throw a ball in this direction with respect to this cart which is moving with v velocity. You throw the ball with some velocity v1 with respect to this cart. On this cart, when you are throwing this ball, you measure that the speed of this ball is, the ball is here, the speed of this ball is v1. Then with respect to a ground observer, he will find that the cart is moving with v, and he has thrown with v1 velocity. So the two velocities must add, and the final velocity, resultant velocity, must be the vector sum. If they are parallel, then it will be v plus v1. So velocity with respect to this observer and this observer is deferred. Now suppose that instead of throwing a ball, he shines a beam of light or a torch. So a beam of light is moving in this direction. He has a torch or something and he put it on, and a beam of light comes out with a velocity c. So with this observer, using the Galilean view, we can say that the speed of this beam of light must be Vr equal to c, which is with respect to this cart, plus the velocity of this cart. But it is not exactly correct. This is the Galilean view, but in a special relativity we find that this Vr is c with respect to this observer on the cart who has the lamp with or the torch with him. He will measure that the beam of light is going with c, and he will also measure that the beam of light is going with c. So this is the principle of constancy of light, that speed of light is not relative to anybody, and the speed of light in free space has the same value c in all inertial system. So if it is going with some constant velocity, so it is an inertial frame, and for that the beam of light will be same, and for that person the beam of light will be going with a velocity c. So this is the constancy of light. Now we have also seen that that there is some relativity of simultaneity. Relativity of simultaneity. We say that if two events are happening at the same moment of time for one observer, then for another observer these two events which are happening simultaneously cannot happen simultaneously. So the fact that the events can be simultaneous is limited to a certain observer, and another observer can see that or observe that the events are happening at different moments of time. So for that you can imagine that there is a spaceship. Okay, so a spaceship is going in space with some constant velocity v. So it's going in a straight line with this speed v. Now there are two emitters which can emit a signal of light, and these signals are observed by an observer O, which is here at the center of the spaceship. This spaceship is very long, you can imagine. It's just a thought experiment. So here is the observer, and this signal A and B, we are naming the points as A and B. Now to specify that these two events occur at the same time, so if a beam of light comes from this point and a beam of light comes from this point, because both of them, light is an electromagnetic wave, so any electromagnetic wave which has been emitted simultaneously will reach this point O at the same moment of time. So in this way this observer will find that both the signals reach here at this point O simultaneously, and because he has already measured that the distance between the two are same, he has measured these distances in advance, and after that he is doing the experiment, and if the two signals come to simultaneously to the observer O, so he knows that the distances are same and the signals are reaching simultaneously. So, and though these two signals are the signals of light, so these signals must have the same velocity, and since they have come simultaneously, so the events have occurred simultaneously. The event of emission of these signals from point A and B have occurred simultaneously. And one thing you must have to say that this V, I just forgot to specify that initially this V is 0. This V is 0, that the space is at rest with some observer on, like this on Earth there is some observer who is watching this spaceship. So initially the spaceship is not moving, there is no exhaust coming out from the propellant fuel. So this spaceship has no velocity with respect to some observer. So the beam of light which is going from here to there and which is going from here to there, both will reach simultaneously because everything is at rest. Now we go to the another case when this V is not 0. When this V is not 0, then the spaceship is moving in this direction. So when this beam of light moves or the you can imagine that the beam of light is like a wave front. So because since this spaceship has moved, so this point must have like this, it has moved by some distance, so this A point will have new position A prime, and this B point will have a new position B prime. This will be the situation. Okay, so the B point must be here. So this is the location of this B point. Now you can see that since the spaceship has moved, this beam has to travel a shorter distance. This beam, the beam from B has to travel a shorter distance as compared to this A. So for the observer who is inside a moving spaceship, will find that the two events are not simultaneous. So you can say that if the spaceship is at rest and the two events occur together, then this observer will say that the two beams reach simultaneously. But for the same case, if the rocket or the spaceship is moving in a direction and the two events occur simultaneously with this observer, with this ground observer, but for this observer he will find that this beam is coming later than this beam, because this distance is reduced and this distance is increased. So he will find that the two beams are not coming together, or you can say that the two events are not occurring simultaneously. So we can say that the two events can be simultaneous for one observer but cannot be simultaneous for another observer. So this is called the relativity of simultaneity. So we find that the notion of time is different for the case of a special theory of relativity. How the time is defined in Galilean transformation or in the Galilean physics or Newtonian physics is different than for the special theory of relativity. So we have seen that time is somehow connected with the speed with which a frame or an observer is moving. For one observer, the two events can be simultaneous, and for another observer, it cannot be simultaneous. We have seen that an interval of time can be different for one observer and can be different for another observer in the effect of time dilation. So we see that in a special theory of relativity, time is somehow related with the motion of the observer. So and the Galilean transformation is not sufficient to explain this phenomenon, that how time dilates. So we need some another kind of transformation equations which can define time with respect to the motion of observer. So for an observer at rest or for an observer in a motion, how the intervals of time can be different has to be defined with some transformation equation, and we know that these transformation equations are Lorentz transformation, which are somewhat similar with the Galilean transformation equations. We need some kind of transformation equations like Galilean transformation equations, but which says that how the time will also transform with the motion of observer. So to define such a transformation, we have to assume certain aspects of time and space, and that aspect is the homogeneity of space and time. So we will see what is homogeneity of space and time and how it affects the transformation equation. So the homogeneity of space and time is basically it basically says that the space and time are, it says that all points in space and time are equivalent. So let's write some equations based on our assumption and similarity with the Galilean transformation. So in Galilean transformation, we know that time is absolute, it doesn't depend on the motion. So there was no such equation between the positions or the velocity relating with the time. But in Lorentz transformation equation, we will write those equations which say that time is somehow related with the velocity. So there are two frames. Let's assume a frame like this. This frame is S with this origin O, and there is another frame which is lying initially at the same, which coincide with the same frame, and that is S prime. But this is X axis, Y and Z. But this frame is moving like this. After some time, the frame must have moved by a finite distance. So this is your S prime frame, and it has moved some distance, which this frame is moving with a velocity v in a straight line parallel with the X axis, and this is X prime. So X prime and X are basically coinciding. So this distance must be v into t. With respect to this observer, this distance is vt. Observer which is at rest is measuring some time, and he will see that this frame has moved, and or the observer is sitting inside this frame is moving. So he must have moved with this distance vt with respect to this S observer. So now just erase this S prime. So this is the situation. Now we have some point P in space. So the coordinates of these points can be X, Y and Z with respect to this frame, but with respect to this frame it will be X prime, Y prime, Z prime. So for the observers in these two frames, they will say that the coordinates of these points are different. For this observer, the coordinates will remain same, but as this frame is moving, he will find that the coordinates are changing. So for this observer, if this point is at rest, so for another observer this point can be moving in opposite direction. So let's assume some equation similar to the Galilean equations. So for observer in prime frame, he will notice that X prime is dependent on all the components, not only on the t. So we will assume some coefficient a11 x plus a12 y plus a13 z plus a14 t. So in Galilean transformation, x was only related with x prime was related with x and t. But here we are assuming that there may be some dependence of y coordinates and z. We are assuming that x is dependent on every coordinate. By assumption, we are not making it any special kind of case. So this is the x prime. Similarly, you can write the y prime. So its coefficient will be 21x plus a22y plus a23z plus a2, this is 24t. So y is depending on all the coordinates of prime framed are dependent on all the coordinates of unprimed framed. This is our assumption, and there is nothing nothing wrong in assuming this equation. We will discuss that why this equation is linear, not quadratic or cubic. We will see this. So let's assume that the another z prime is equal to a 31x plus a 32y plus a 33z plus a 34t. And for the time, so this is the special one, because in Galilean transformation equation or Newtonian mechanics, we know that time is absolute. It doesn't depend upon anything. Time is absolute for the whole of the universe. But here we will find that the time depends upon the observers. So let's call it a41x plus a42y plus a43z plus a44t. There cannot be dependence between the two. There may not be a dependence between some of the primed and unprimed coordinates, but by default we are assuming that there is a dependence, and if there is no dependence, then some of the coefficient may be 0. So from starting we are not assuming any kind of a special case. Only the special case is that this coordinate frame is moving parallel with this, and there is nothing wrong with it, because if you assume that this coordinate is moving with some angular velocity, it is moving with some angle, not angular velocity, with some angle, then these coordinates will transform in a different way, but the basic physics will remain the same. So we are taking the simplest of the simplest case, and which is this. So why these equations are only linear? Why we are not considering equations like an square with this? Let's assume one of them. So let's consider that this x prime depends upon a11x square. So why this is not a possibility for a transformation equation for an inertial frame? So let's see this. So consider that there are 2 points in a space which are separated by a distance of 1 unit. So this is your x1 coordinate and this is x2 coordinate. So in one of the frames, like we could have imagined it here like this. This point has coordinate x1 and this is x2, or you can consider it on the same line, anywhere you can see. So with respect to this s prime, there must be a prime here, and with respect to this there will be no prime, but the distance between the two is same, so which is 1 unit. So if you want to define this x1 prime, and you are assuming that the equation transform in this way, it has a square term, so it will be a11 into this x1 square. So just assume that this x1 is having value 1 and this is having value 2. So if you subtract them, 2 minus 1 will be 1. Or you can have this value as 2 and this as 3. So again, if you subtract the coordinates 3 minus 2, the length will be 1, and just it is parallel with the x-axis, or it will not work. So in that case, if x1 is 1, so x1 prime will be equal to a11 into 1 square. x2 prime will be equal to a11 into 2 square. now if you do for these, so you will get that x1 prime is a11 into 2 square and x2 prime is a11 into 3 square. So if you subtract, what is the meaning of writing like this? It simply says that this is the coordinate system. If you put 1, 2, 3, if you put a rod here, so left coordinate x1 will be here and x2 will be here in some coordinate frame, and you are calculating it in another frame. Now if you put this rod not here but here, just hold this rod from here and just put it here, like remove it from this point and put it here. Okay, so we are just changing the position of this rod AB from this position to that position AB. Okay, so just by putting the rod at different positions can change its size. You will see it here. So now you calculate this x2 1 prime minus x1 1 prime for this case. So you will get that x2 prime minus x1 prime is equal to a11, this will be 4 minus 1, which is equal to 3a11. But if you calculate from this, so this is x2 prime minus x1 prime will be equal to a11 9 minus 4, so this is 5a11. So you see that just by putting the rod from one position to another position in some S frame, for the primed frame the size of the rod changes. If you put the rod in this position, its length is, if its length is 1, or if its length is this length is 1, if the length of the rod AB is 1 in S frame, then its length in S prime frame will be this 3a11 with respect to if it is placed between these 2 points. But if you place that rod here between 2 and 3 in S frame, then this rod in S prime frame, its length measured will be 5a11. So it's not possible that just by putting the rod at different position can change the length of the rod. So it is again the principle of homogeneity, that all the these points are not special, that if you put it here its length will be different, and if you put it here the length will change. So this is called the principle of homogeneity, that all points are same, and to satisfy this principle of homogeneity you have to assume that this transformation equation cannot be correct. The correct transformation equation must be linear in x, y, z and t, and if it is not linear in x, y, z and t, then just putting the rod at different position in a coordinate system will change. Just like if the pen is here and if I put the pen here, the length will change. So it cannot change for any observer, because for the same observer it will change. For the S prime observer the length will change, and it is not possible by just putting the rod at different position can change the length of the rod. So this goes against the principle of homogeneity, which says that all points in space and time are equivalent, and this is one of the most important concept in special theory of relativity, because without this assumption you cannot arrive at the Lorentz transformation equation. Or you can also say that the Lorentz transformation equations are those equations which can maintain the constancy of light, the principle of relativity, and the principle of homogeneity of space and time. So these are those equations. These equations will convert to, these are not those equations. It is a general way of thinking that the equation the Lorentz transformation equation can be represented by this kind of equation, and our work will be to find these coefficient, and if we have already found this coefficient, then we will be defining the Lorentz transformation equation. So let's try to find these coefficients. So if you simply think that this observer is not moving, so from the start these two frames will coincide at this O point. This is O prime, so O and O prime will coincide, and you will see that all the coordinates will be same. This point will have the same coordinate for the two observers, because the two frames are coinciding. So in that case x prime will be equal to x. So in that case x prime, this a11 will become 1 and rest will become 0. a12, a13 and a14 will be 0. Similarly y prime will be equal to y, because the two are same. The two frames are exactly same. If v is 0, then this a11 will be equal to a22 is equal to a33 is equal to a44 equal to 1. T prime and t will be same also. So these coefficients will be equal to 1 and all other coefficients will be 0. Otherwise it will be wrong. Now this is one of the case when this S prime frame is not moving. Another case is that if it is moving with a velocity which is very very less than the speed of light, like for the Galilean transformation case. So the Lorentz transformation which we will derive must become the Galilean transformation equation for the case if V is much less than C. The Galilean transformation equation must convert into the Galilean transformation equation. So these are some of the patterns which this transformation equation should satisfy. So it will be a very long task to find this all 16 coefficient, and we will be moving with a consistent way. So let's start with finding some of the coefficient. So first you assume that the x-axis and x prime axis coincide. So if the two axes coincide, x prime and x coinciding, then this length, this height or the y coordinate should not change. So you can say that for x and x prime coinciding, because they are coinciding, then if for a point which is lying on this x-axis, suppose this point which we have taken at this point with some height. Now consider that this point lies on, we consider a special point which is lying on this x or x prime axis, because both are coinciding. So for those points which are lying on x or x prime axis, the y coordinate and z coordinate must be 0 on x axis. So if y and x coordinates are 0 in S frame, then this implies that in the S prime frame, these y prime and z prime must also be 0, because these coordinates are not going to change, only the x coordinate is going to change. So with how much velocity this s prime frame is moving, it doesn't matter, this point will always remain on this x-axis. Okay, so we can put these things in the in this equation which we are calling equation 1. This set of equations are equation 1. So if you put this in here in the second or in the third equation, you will get that y prime and z prime are 0 for y and z being 0. Just put these values as 0. So if I put it 0, then it will be a21x plus, now this y is 0, so this term will become 0. So just write it 0, or just skip the term and write directly a23, and this term is also 0 because z is 0. So these two terms, you just remove these terms. So the another term is a24t. We are not considering the t, we are just putting these values. So you get like this. So in the left hand side you have 0, and in the right hand side you have these two terms. Now you know that since this there is some, this is x prime and this is your x, so x or x prime cannot be 0 and time must have elapsed. So these t and x and t cannot be 0. It was 0 in the starting when the two frames were coinciding, but after some time these two values are not 0. So this means that for the left hand, for the both of the side to agree each other, this means that a21 equal to 0 and a24 must be 0. So just by observing this simple fact, we have found these two coefficients. Okay, these two coefficients, we have seen that these two are 0. And similarly you can say that if the frame is moving in x-axis, then the y coordinates are not changing. Similarly the z coordinates will also not change. So we can apply the same concept for this equation. So if you put z prime equals to 0, then you get a31x plus, this is 0 because y and z are 0 on x-axis and z prime is also 0. So these two terms goes, and this is a34 into t. So for this equation to be true, a31 equals a34 equals 0. For this case these two terms are 0. So if these two terms are 0, the terms which are 0, we will be removing those terms, just wipe out those terms. So let's start doing this. So first we have found that a21 is 0, so just cut this term. So a21 is 0, so this is meaningless to write this term. So now a24 is 0, this term goes off. Now these two terms a31, this goes off and this a34 goes off. So now you have a very simple equation for y prime and z prime. What will happen to x prime and t prime, we will see it later, but for now this just write these two equations separately. So we have y prime equals a22y plus a23y, so a23z, we have a23z here. So you have to just get rid of these unnecessary terms. So now this z prime will be equal to a32y plus A33Z. So now these two terms have become, these two equations are now looking very simpler according to the compared with the previous one. Now just see that this xy plane. In xy plane you will find that in this plane z is 0. So for a point which is lying in this xy plane, because this point is lying in xy plane, this point, so for that point which is lying in this xy plane, the z coordinate is 0. And if z coordinate is 0 in S frame, it is not going to change in S prime frame, because by moving this coordinate system only x can change and this z value cannot change. So if in xy plane z is equal to 0, this implies in S frame you have to write in S frame z is 0. This implies that in S prime frame or the in x prime y prime frame plane in x prime y prime plane, this z prime must also be 0. So from here you get it. Now just put these values here. So z prime is 0, put it here. So z prime is 0. This implies that A32 y plus this A33, this term is 0. So this means that both terms, this is 0, but for left hand side is, if the left hand side is 0, this term must also be 0, and it is only possible if A32 is 0. So this, we have calculated this term A32, so you can cancel this term also A32. So we will do it here. Now similarly for the xz plane, in the xz plane, not frame, xz plane, you have y equals 0. So for in x prime z prime plane, the y prime, this implies y prime must also be 0. So just put it here. So if y prime is 0, if y prime is 0, you can write it A22y. This y is 0, so just this term will become 0. So y, this is 0, so it goes off. So only this term will remain, A23. So in xz plane, y will be 0. X and z can have some value, but in xz plane y must be 0, and if y is 0, so y prime must also be 0 in the S prime frame. So this is 0, this is already 0, and this will remain. So for this equation to be true, this term z is not 0, z can be 0 or not 0, but this must have to be 0. So A23 must be 0. So the two terms A23 and 32 are 0. So just cut out these terms. So A23 goes off and A32 and A23 goes. So now we have the transformation equations as, from here you get y prime equals, this term is 0, so this is equal to A22y. So this is one of the transformation equation. So this transformation equation has been replaced by this one, and this transformation equation is z prime equal to a32 is 0, so this is equal to a33z. So you have this another transformation equation. So these three terms become 0, and only this a22 coefficient will remain. Similarly, a33 coefficient is remaining and rest are 0. So we have done much for these two, but now it's time to do for these two transformation equations. So let's see this. Now let's consider that there is a rod of length or a length interval. Just consider a rod with a unit length. Consider a rod of length 1 meter. So now I have replaced these equations by those which we have arrived previously. So now consider a rod of length 1 unit. Now if the frame is moving, you know that the x coordinates change, but the y coordinates remain same. So if you write these equations in that way, then you will find that consider that if y is equal to 1, this length is 1 with respect to s observer, not in the s prime observer. Consider that this rod is of length 1 unit for s observer. So we have y equals 1 and just put it there. So y prime will be equal to a22 into 1. Now for the s prime observer, if y prime is equal to 1, because the two are not going to change, then just put it there. Then if y prime is equal to 1, then 1 will be equal to a22 into y. So from here you can calculate that y prime is equal to a22, and from here you will calculate that y is equal to 1 upon a22. So you know that the length of the rod remains same for the two observers, because the only x coordinates will change and there will be no effect in the y coordinate, as we have already seen these in the length contraction formula, that the length will only be contracted for if the length only those lengths will be contracted which were in the direction of the velocity of the observer, but this is perpendicular to the velocity of the observer. So there will be no length contraction in this direction. So this y and y prime are same, so you can write it that this a22 will be equal to 1 upon a22. So from that argument you get that a22 square equals 1, and this implies a22 equal to 1. And similarly for this equation, so you can also say that a33 is equal to 1. So finally these two equations will become y prime equals y and z prime equals z, which were same for the Galilean transformation also. So we have found all the 4 coefficients of this equation and this equation. So we have already found 8 coefficients, in which the 6 are 0 and 2 are 1. Okay. So now just come to this 4th equation for the t prime. Now consider that there is a clock here and there is another clock which is here. there are two clocks. So this is clock C1 and this is C2. These two clocks have been placed at an equal distance with respect to the origin in the positive y-axis and negative y-axis. So for these symmetrically placed clocks, they will measure the same interval of time. For S observer, if you put two clocks here also, then you can say that these two clocks can disagree and these two clocks can disagree, but these two clocks cannot disagree, and these two cannot disagree with each other. If they are synchronized initially they are synchronized and these two are synchronized, then they cannot disagree. They can disagree that the times are different, but these two times will be same. So what this says for the fourth equation, you can say that this furthur term, this A furthur term must be 0. Why? Because if it is not 0, then placing the clock in positive y-axis at a certain distance or placing it in the negative y-axis with the same distance will change the time in the clock. Because if you put positive y, suppose you put y equals 2, then the time t prime will be different. So for this S prime observer, he will find that the time in this clock, in the observer who is sitting here will say that the time in this clock is different with respect to this clock, because you will put here for this clock you will put -2 and for this clock you will put +2. So the t prime values for these two clocks will change with respect to this S prime observer. But this cannot be possible, because the two clocks will measure the same time and it will also violate the homogeneity principle, that all the points in a space and time are equivalent. So there is no special footage for this position, that if you place the clock here it will move faster, and if you place the clock here so because this is negative, the clock will measure some lesser time for this S prime observer. This is not the case. This is not possible. So the two clocks must measure the same interval of time, and for that this term should not be here. So the dependence on y should not be there, otherwise it will violate the homogeneity of space and time. Here the homogeneity of a space will be violated, because putting it at different locations in the same coordinate system is changing the time in the S prime frame. So A furthur must be 0. And similarly for Z axis, if you put a clock here or put a clock here, it doesn't matter, both will measure the same interval of time for this observer and for that observer also. The interval of time measured by an observer in this frame can differ from that observer, but for any one of the observer, the two clocks must measure the same interval of time. For this observer, the two clocks must measure the same interval of time. So this A43 must be 0. So now you get rid of these two terms. So t prime equation becomes A41x plus A44t. This is the final equation, the fourth equation. So you have these two equations simplified and the fourth equation. Now come on to the first equation. Now for the first equation, you can do it by a simple argument that if a rod is here, so you measure if there is a rod here and both the frames start from here and the rod has some length, okay, or just take a point. There is a point x, so it has some distance d or something. Then with respect to this observer, that this distance will remain same, but for the other observer, the s prime observer, the coordinates of this point is changing. Now consider that this point, instead of here, you put it here, you put this point here. So for this point, the x-axis is changing, the length of this will change as this this coordinate system is moving. So this length is going to change only, it is decreasing, and after then it will be in the negative direction. So only this length is changing, and this y and z, there is no dependence of y and z on x-axis. This x prime is only dependent, this x prime is only dependent on this x and t, and not on y. So these two terms should go, because there is no dependence of y and z coordinates on x. With respect to time, the x coordinate can change, but there is no dependence with respect to y and z for the x prime. So we can say that this x prime becomes equal to a11x plus a14t. So you know that initially that this s prime frame was coinciding with this. So with for the observer in s frame, he will notice that it has moved by a certain distance d, which will be equal to the velocity with which this frame is moving, v, and the time which has elapsed. So, and for this observer, so this will be this distance d will be the x coordinate for this point. This point, this is not the x. Now we consider that this is the x. Okay, this is your x or the d. So this the distance by which the s prime frame has moved is the x distance or the d distance, which will be equal to vt. And for this s prime observer, the coordinate of the same point is 0. So x prime is 0. So for this s observer, the x is the coordinate of this point is d or vt. But for the s prime observer, the coordinate x prime is 0, because it's the origin for this s prime frame. So you can say that for x prime to be 0, this x should be equal to vt. If x is equal to vt, this implies x prime is equal to 0. The coordinate lies, if this coordinate is 0, then for that it will be equal to vt. So the two distances will be we can calculate. For this it is 0, and for that it is vt. So if you put this in this x prime equation, so you will get that x prime is equal to 0, put it here, will be equal to a11, and put vt instead of x. So put here vt plus a14t. So you get that a14 into t is equal to minus a11 vt. You can cancel these t terms, because we are interested in calculating the coefficient. So a14 will be equal to minus a11 into v. So now we have calculated the a14 coefficient. So now we will finally write our equation. So these two we are get rid of. We have calculated this A14 and the rest we are writing here. So the final equations are x prime is equal to s prime equals A11x plus, no, it's minus, so write it minus A14 is equal to minus A11v. Okay, and there is t. So this is A11, you can take a common A11 x minus vt. So this is what we have got. This is the first equation. The second is y prime is equal to y and z prime is equal to z, and for the t prime equation we have t prime is equal to A41x plus A44t. So we can say that from the 16 coefficient we have the remaining are only we have calculated most of them, but only these A11, A41 and A44, these three equations, these three coefficients we have to find. So if there is confusion, I'm just telling for the second time that the coordinate system has moved by some distance which is d. So for this S observer, the coordinate of this point will be d, or x will be equal to d. Now this distance d will be equal to vt for this observer. So x is equal to vt for this observer. The location of this point is vt, but for that observer it is his origin, so he will say that x prime is 0. So we have put these values x equal to vt and x prime equal to 0 in this equation, and we have got this equation. So if you closely observe, you will find that what we have done till now is the two things we have done. The first is we have applied the principle of relativity, that the laws of physics are same for all observers in inertial frames. So that's why we are saying that for two observers the length will be same or something like that. But and another thing, the homogeneity of space and time, because for the two clocks should be measuring the same interval of time. This comes from the homogeneity. The Lorentz transformation equation should be linear, and this comes from the homogeneity principle. The third thing which we have not applied yet is the constancy of the velocity of light. So let's apply the constancy of velocity of light, and applying that we will be finding these three coefficients. Without that we cannot find these coefficients, because from the arguments we have rejected some of the coefficient and put them to be 0. But these coefficients cannot be removed by those arguments, because it needs something more, it needs more elaboration in terms of the constancy of the speed of light. So now consider that the two frames coincide initially, the S and the S prime frame, and when they are coinciding there is a spherical wave front which is expanding. There is a source of light which is emitting a spherical wave front, and the wave fronts are becoming larger and larger. It's a spherical ripple of light, so it will becoming larger and larger, and as it become larger the frame is also moving. So the S prime frame, S is remaining here, and S prime frame has moved from this point to this position to that position. This is S prime, and for that time the sphere would have become considerably larger, like this. The sphere has become larger, the wave front has reached here. So consider a point P on this sphere. Then if you apply some geometry, then you will find that this x square plus y square plus z square with respect to this S frame will be equal to c square t square. It will be an equation of this expanding sphere. As time is elapsing, these x, y, z are changing, and this radius, which is ct, which is because this is expanding with a velocity of with the speed of light, so the radius must be c into t. That radius must be equal to x square plus y square plus z square. So it's the equation of an expanding sphere. But for this S prime observer, he will say that the coordinates of point P will be x prime, y prime and z prime. So he will square these three terms and will say, and he will also measure a different time than this, because you know that when you move, the time measured can be different in a special relativity. So this is c and t prime square. So for S observer, the coordinates are x prime, y prime, z prime and t prime, and for the S observer these are x, y, z and t. So both can write the equation of this expanding wavefront sphere in this way. So now we have this transformation equation x prime, y prime, z prime, t prime. Now we will put these primed coordinates here in the second equation. So let's put these terms in the second equation. So if you put x prime here, then you will get that a11 into x minus vt. Just put it here, and because this is squared, so you have to square here. So the square will come on both the terms. So this is x prime square plus y prime, and y are same, so you can write it y prime is equal to y prime square, y square. Similarly, z prime square will be equal to z square. Just replace z prime square by z, squaring both sides. Okay. So x prime, y prime and z prime will be equal to c. This here square is missing. The c will be same for the two. This radius r is given by velocity of light c into the time taken. So the c will be same for all inertial observers. So both observers will measure the same speed with which this wavefront is expanding. So let's see that this c square into t, instead of t prime we have to put this whole term. So a41 x plus a44 t whole square. So this is the final equation which we will solve, and we will get these coefficients. So if you expand these terms, you will get that a11 square. So from here you get a square, x square term, and from here also you get a square term. Let's combine these two square terms. So this is a11 square and x square. So minus, subtract the square term from here, or just write it simply, then we will do it separately. Okay. So this is x square minus a11 square v square t square, this will be plus, okay, minus 2a11 square x into vt. This is a plus b whole square formula, and with multiplied with this a square, a11 square term. So everything is okay. Plus this y square plus z square will be equal to this square term. So this will be c square, and this will be a41 square x square plus a44 square t square plus 2 into a41 x into a42t. This is what you get. So you have a square term and a square term here. So let's combine these two terms. So you will get a11 square minus c square a41 square, okay, by a bracket of x square. So we have already used these two terms. Now the second term we will write as y square plus z square. We have used these two terms. The terms which I am underlying we have already used. Now you have a vt term here, and you have a x vt term, or remove just v, x and t. So you have an x and t term here. So combine these two. So it has a minus sign, and if we take it to the left hand side, it will become a with minus sign. So just write it in combined form as minus 2 is common, so take out 2, a11 square v, xt will be common, plus this term a41 a42, and rest we have already taken out. So this is x into t. So we have written all the things except the right hand side. So the right hand side will be equal to the remaining term. I have underlined the things which I have already used. So only this term is remaining. So c square a square 44 t square. So this is what we get. No, we have this term also. So just subtract the take it to the right hand side, minus a11 square v square, and this is the t square term. And you can just check it that these two terms combined here, y square and z square as it is. Then this vt term here, xt term, we have combined these two terms by taking it in the left hand side, and this t square term is remaining here. So these two terms I have combined in the right hand side. So we have the final equation here. Now this equation was written in the primed coordinates, and this was in the unprimed coordinate. Now we have converted by using the transformation equation, arbitrary transformation equation, which because these constants have not still has been calculated. So now you can see here that this equation and this equation are the same equations, because they are written in the unprimed frame. And if you compare these two equations, by putting this transformation equation, we are writing this equation of the sphere in the unprimed frame. So from the unprimed frame, this is the equation, but after applying the transformation equation, we are getting this. So this equation and this must be the same. So we can compare these two equations, and on comparison you will find that there is no xt term in this. So the coefficient of xt, this term, this coefficient must be 0. So the first thing you can see that a11 squared v plus a41 a42 must be 0. This is the first thing which we can see on a simple inspection, because there is no crossed term of x and t. There is no cross term, only separate terms of x, y and z. Although it is in quadratic term, but we have not here any x and t term multiplied simultaneously. So this is the first equation which we observe here. Is anything missing? Yeah, there is one thing which is missing. We have not multiplied this c square term here. The c square must be multiplied here, because when we have multiplied here, we have the c square term, but we are not multiplied c square. So there is a c square term in the a41 a42 product. So here is a c square missing. So just I box this term. Now this coefficient of x square is 1 here. So this term must be equal to 1. So there is another equation which is a11 square minus c square a square 41 should be equal to 1. So we have another equation. I just keep enclose it in a box, in a rectangular box. So a11 square minus c square a square 41 is equal to 1. So you have these two equations. Now is anything else? So y square and z square are same here. So we have one thing, this coefficient, the coefficient of this t square term must be equal to c square. So you can write the third equation as c square a square 44 minus a11 square v square is equal to this c square. So c square a44 square minus a11 square v square should be equal to c square. So we get these three equations by comparison of comparison of these two same kind of equations of spheres. So now our work will be to find this coefficient by